Akash, and today I will be presenting our work on joint rolling shutter correction and super resolution. CMOS cameras are popular for mobile application due to their low cost, reduced power consumption, and compact design. However, CMOS cameras have rolling shutter rather than global shutter. This causes rolling shutter artifact in the captured image. Example of a rolling shutter artifact is shown on bottom right. Another issue with mobile capture videos is their compatibility with high resolution displays. Most of the existing super resolution method assumes that the input video is global shutter, which may not be true for videos captured using rolling shutter cameras. Thus, addressing the problem of joint rolling shutter correction and super resolution becomes critical. Some works have tried to address the task of rolling shutter correction and super resolution independently. However, in this work, we address this task jointly by leveraging local pixel level attention using deformable convolution and exploit patch recurrence property using global patch level attention in the latent space. In this work, given low resolution input video frames with rolling shutter artifacts, we extract features representation corresponding to the central frame VI using the encoder network and flow features with respect to the past frame and future frame. Patch attention network then takes these features as input and utilizes deformable convolution and patch level attention to obtain high resolution feature Z that can recover global shutter image. The high resolution feature Z is then used by a decoder network to produce high resolution global shutter frames. In the next slide, we will discuss patch attention network in detail. This is the encoder features and flow features to incorporate motion information at pixel level. Then output of deformable attention along with flow features are unfolded into patches and patch level attention is computed using equations shown here. Followed by passing the feature through a super resolution layer to obtain high resolution feature, which is then used by the decoder to generate high resolution global shutter frames. As patch attention network is the first work to address the task of joint rolling shutter correction and super resolution, we compare our work with cascade of state-of-the-art rolling shutter correction and super resolution works. We can see that our approach outperforms all the cascade approach. We also compare our work with state-of-the-art rolling shutter correction method where the rolling shutter correction method takes high resolution input. It is interesting to see that PatchNet outperforms this method even when the input to our model is low resolution frames. Since we leverage patch attention, we study the impact of patch size in our patch attention mechanism. We found that with smaller patches, performance of our model is poor. However, we see improvement of about 2 dB in PSNR when we increase patch size from 2x2 to 8x8. Here are some qualitative results of our method on BS-RSCD videos. We can see that our proposed approach is able to recover text well in this particular example. Another example where our model is able to recover high resolution global shutter frame from low resolution rolling shutter frames. And patch attention network to recover high resolution global shutter frames from low resolution rolling shutter videos. Unlike existing approach, our work learns the rolling shutter correction and super resolution through attention mechanism. The proposed approach employs patch level attention in feature space to extract global information from neighboring patches using the key query similarity and local information using deformable convolution.